Hi, everybody. So some of you have probably heard the name and wondered what it means. What are the rare earth elements? They're a very important group of elements in geology. They are so frequently referred to that we almost always use the shorthand RE. That is very, very common in the earth sciences. So the rare earth elements are these guys down here at the bottom of the table. They begin with the element lanthanum. Lanthanum could also be slotted in over here as element number 57. And for that reason, these are also called the lanthanides. And just above those, or excuse me, just below those are the actinides. And there's some very important elements in geology here. Thorium, uranium, you've heard of, very important for age dating, as are some of these other fellows like palladium and actinium. Anyway, we're going to focus on these guys here, the rare earth elements. So what is special about those? Well, what's special about both of these rows is this is where we're filling in the f orbitals. The f orbitals are pretty much left empty until we get all the way down here to element number 57, lanthanum. It's only there that we begin filling in the f orbitals. So that's 57 protons. That's a lot of protons you got to bring in to a nucleus before you start filling in the f orbitals. But come back to this diagram in Klein and Dutrow. Take a look at this. When we start filling in the 4f orbitals, that's the first place that those f orbitals arise. They are also almost identical in energy to the 5d orbitals. And the 4f and the 5d are actually splitting the energy of the 6s and the 6p orbitals. So there's a little bit of craziness in terms of the energy levels that the electrons are choosing when they're trying to find that lowest energy level. Where are they going to go? Well, for the rare earth elements, it's very common for them to have an electron configuration with something like 5p6, 5d1, and then 6, S2. And then the 4F, X number of electrons will go in there as we go from left to right. So we've got the 4F electrons being filled, but by the time we get to the 4F, we've already put in 2 electrons in the 6th row. Let's count these out. 1, 2, 3, 4, 5, 6. So that's the 6th row where lanthanum is. So by the time you get to these, those 2 6s orbital slots have been filled. There's a 5d1 slot that gets filled in lanthanum. And then the 5p slots have been filled. And then we start filling in these 4f. But if you take a look at these guys that are sitting out here, these 2 electrons in the s and the 1 electron in the d orbital, it's very easy for those to get pulled away by, again, an atom like oxygen that's happy to take up electrons anywhere it can find it. And if you strip away 3 electrons, then you end up with a 3+ charge. And almost all of the elements here will typically have a 3+ charge. Now, not all of them. They can have other charges. Actually, they can all have a 3+ charge. I think cerium can be +2 or +4. Europium can be +3, +2 as well as +3. But the 3+ charge is very, very common. And that's important because there's something else going on with this group. And that is the so-called Lanthanide contraction. So what the Lanthanide contraction means is this. We have 57 protons in the nucleus for lanthanum, and we gradually go up in increments of 1 to 71 protons over here at lutetium. So if you have a 3+ charge, a constant charge, but a growing number of protons in the nucleus, those greater number of protons can pull those electrons into a tighter and tighter orbit. So lanthanum ends up being a very large atom, while lutetium ends up being kind of small. So that means that we can do some really interesting experiments, both in the lab and in nature. So let's say you have a crystal structure that looks like this. And I'm going to draw a cube because I don't have a lot of artistic skill. So here's a cube. There's a bunch of atoms that make up the corner. Maybe there's an atom that can fit in the middle of that cube. And let's say there's a cube of a much different size. Let's say this guy over here has a type of structure where the bonds are much longer. And so we end up with a much bigger space in the middle of this little crystalline structure than we do over here. So we have crystal number 1 and crystal number 2. Well, if the charge that's required for charge balance is 3+ in both cases, then the only thing that will determine what kind of element will go there, if you're choosing only amongst the rare earth elements, is the size. A very large atom like lanthanum or cerium might fit well here, but these guys would be too small and they'd rattle around. But these big fellows here won't fit into the structure there, but the tinier ytterbium and lutetium might fit very well into that structure. And so that means in both nature and in the lab, we could do experiments where we could test what kinds of crystal structures will absorb what kinds of elements. It allows us to do experiments where we can work safely and say, oh, this structure will take an element of such and such size. And then you could think about whether or not you could put in something more dangerous, like a poisonous metal or something that's radioactive to be able to get it out of a wastewater stream. Or there are things in nature where they could tell us really interesting things about how much oxygen is in a system. So for example, europium, like any other rare earth element, is usually 3+, but if there's not a lot of oxygen around, it might only be in the 2+ state. And when it's in the 2+ state, its radius is about the same size as calcium. So calcium, that should also be 2+. Europium and calcium can easily substitute for one another in various kinds of crystal structures if europium is in this 2+ state. If there's a lot of oxygen around, though, pulling away electrons, then europium will be in the 3+ state, and it won't be able to make that substitution because it will be the wrong charge. And so that's another way we can use the rare earth elements, is kind of an oxybarometer. How much oxygen is in the system? We can make those kinds of tests by looking at, let's say, a europium and calcium exchange and see how far that exchange goes. If it goes to a great extent, then it could mean that there's less oxygen around. We have a lot of europium 2+. And if there's lots of oxygen around, then europium, there, I finally said it correctly the first time, that europium 3+ would indicate that there's abundant oxygen compared to an environment that has a much more significant europium-calcium exchange.